Okay, at the end of the previous video, I asked you to calculate the variance in this example when we have $1 fee. And then let's do this together. So the first, remember, I will calculate the mean and deviation and square the deviation and calculate the mean of squared deviation. That's how we are going to calculate the variance. First, the mean. We get new outcomes like this, and their probabilities do not change. So multiply to obtain minus 2.2 probability weighted outcome, and minus 1 times 0.4 minus 0.4 plus 19 times 0.4 equals 7.6. So we get 3 probability weighted outcomes, and if you sum, then you will get 5. The mean is 5. Remember, the previous example had mean equals 6, but now after a $1 fee, we get 5 because, as I said, you pay $1 fee, right? So the difference is coming from the fee, but let's just keep doing the variance. We are going to calculate the deviations, right? So we will, so remember the mean was 5 in this numerical example. So from these outcomes, we are going to subtract 5 and we obtain deviations. So minus 11 minus 5 equals minus 16. Minus 1 minus 5 equals minus 6. Positive 19 minus 5 equals 14. Okay, so we get a new random variable named deviations. And then we will square them to calculate the square deviations. By the way, so these numbers are squares, but you remember these numbers are same as before. Excuse me. So the deviations and the square deviations are identical to here, square deviations and deviations, square deviations, right? So back to the new case, we get the same deviations and square deviations. That's because we are paying, and as a result, by the way, as a result, the variance, like after you calculate the square deviations times probability, so that is probability weighted square deviations for each outcome like this, multiply, so we get these 3 numbers. You can use a calculator here. Then we will get the same variance. You don't need to do it again because those numbers are exactly the same as the previous example. Okay, so the variance does not change. That is the result. Excuse me. So the variance does not change. Let me think about it. Why the variance is the same? The reason is here, the mean was different. Mean was different due to the fee. Okay, $1, you are paying additional $1, so the mean is lower by $1. But at the same time, your gain and your losses are also $1 lower than before, right? So everything is moving. Say if there is a distribution like this, everything is moving to minus 1. Okay, so however, what we are interested in is we are just looking at the spread variability. It does not change. It's parallel shift. So everything, your gains and losses take minus 1, but also the mean takes minus 1. So the deviations, the distance does not change. That's the reason why you get the same variance here. Okay, I'll come back to this point later. So now, let's think about another example. from the original investment, I'm going to just increase my investment by 10 times, right? Previously, the original was minus 10, 0, and plus 20, but because I invest 10 times more, all the gains and losses are also scaled by 10, okay? So minus 100, 0, and plus 200. Before going to the next page, I want you to calculate the variance of this example by yourself, right? Or at least guess how the variance will change. It may not change. So the original variance was 144. So when you increase the scale, how would the variance change? Okay. So stop the video if you need time to calculate the variance. But let me turn the page. So we will just do the same thing. We will calculate the mean as the first step. Outcome, probability weighted outcome. Okay, and outcome, probability weighted outcome, same thing. So you get 3 probability weighted outcomes, and their sum is 60. 60 is the mean, right? Remember, the original mean was 6, right? So it is intuitive. The mean becomes 10 times larger. That's because I scaled my investment by 10 times. So everything is amplified, increases by 10 times. Okay, it makes sense. Okay, the next step is to calculate the deviation. Excuse me. Yeah, deviations. So here is the outcomes we get, and we are going to subtract minus 60, like 60, subtract 60, okay? So 100 becomes minus 160, and 0 becomes minus 60, 200 becomes 140. So they are deviations. Okay, up to here, these numbers are exactly 10 times larger than the original example. But let's think about square deviations. We are going to transform like this. When you square the deviations, it is 25,600, right? When you square 160. And when you square 60, it becomes 3,600 and like say 19,600. So the problem here is the square deviations are inflated 100 times. We did nothing wrong here. We are just taking squares. That's because, so here we multiply 10 to the original outcome. So when you calculate the deviation, everything was multiplied by 10. That is natural. But when you square that, everything is multiplied by 10 squared. So that is 100. So square deviations are 100 times larger than the original numerical example. Okay, then let's see the final variance, the variance. So we get the square deviations as a new transformed random variable, and then the probabilities as the original, so no difference. We multiply the outcome, this is new outcome to probability to get this. Outcome times probability, get this. Outcome times probability to get this. Again, you can use a calculator or Excel to do this algebra. So we have 3 probability weighted outcomes, and in the end, you get 14,400. This is the variance. The variance becomes 100 times larger. And the intuition is clear, right? So because we take squares, so multiply by 10 becomes multiply by 10 squared, which is 100. All right? So this is not like, this is nothing wrong with the algebra. This is true. So let me compare the 3 examples. Suppose that the original investment was X, and the new investment y is x minus 1, right? I have to pay $1 upfront, and say z is when I invest 10 times more than the original, right? So y and z are new random variables transformed from the original, okay? And then let's think about the mean. Original is 6, but it is 5, it is 60. This is natural, right? So take minus 1 and multiply 10 is still preserved here. Okay, so from the original, these new expectations, new averages, preserve the same transformation, right? If you take minus 1, do the same thing. If you multiply 10, do the same thing. That is good, right? This is natural and desirable. But the problem is, say, original variance is 144. But I wish it would be natural. You may think the variance should be 144 minus 1 because y is x minus 1, but no. Variance did not change. Variance did not change at all. And here, I would expect a variance multiplied by 10, but no. It is multiplied by 100, right? We saw that, okay? So this is main difference between the variance and the mean. Or in other words, a mean has a very nice properties, many nice properties, well-behaved properties. We are using them without understanding how valuable, how important, how useful they are, right? So that's why the mean is most common statistical measure. It's really nice. So then, let me generalize this theory. So we are going to think about the linear transformation again, as we did in chapter 3. So suppose you have original random variable x, and you are going to change this into y by multiplying a and adding b. All right? So then it is linear transformation. It's linear. Multiply and addition. Okay? So then we learned it. So the mean is pretty simple. You just take the same process, then you will get the mean, right? So if you know the original variable's mean, then the new variable's mean is pretty easy to calculate. But when you calculate the variance, suppose you know the variance of the original random variable, but you are interested in the variance of the new random variable. How can you do that? First, you have to square the multiplicative constant a, right? And ignore the addition. Addition does not appear in the variance, does not affect the variance. This is the rule. And I explained the idea. The first, why the addition does not affect, that's because variance is about the distance. If everything, including the center and all the observations, change parallel, like parallel shift, then the distance does not change, right? Addition does not change the distance. It's only about location. But multiplication is different. Multiply something will scale everything like large or small, right? If you multiply a large number, all the distance will be amplified by the same scale. So that affects both location and variability. So location means the mean, and the variability means the variance. Okay, the variance is affected by the multiplying constant, but it's not ideal. The problem is, but by its square. Okay, so this is the problem. Variance is inflated by a squared, which is not desirable. So we are going to scale it back to preserve the unit, right? So we are going to take the square root of the variance at the end. Then we call that standard deviation. The famous standard deviation is a byproduct of variance. Okay, so it is basically same as variance. If variance increases, of course standard deviation increases too, and vice versa. And it is a measure of variability. The larger the standard deviation is, the more variable your data are, or the observations are further away from the center on average. And it is usually denoted as standard deviation of x, or Greek letter sigma, or alphabet S. And this is the rule, pretty clear. Okay, so we call that unit constant. That means if you multiply a, then standard deviation will be multiplied by a. So multiplication is same, like preserved. Okay, now let's compare the numerical examples again. So the variance, original case, the variance was 144. Its square root is simply 12. All right. And then when you define a new random variable by taking -1, that does not affect standard deviation. That is not surprising, right? But the point here is z is 10 times x, but variance is multiplied by 100. But standard deviation, if you take square root again, then it becomes 10 times larger than before, right? So exactly 10 times, which is desirable. This is the reason why we are going to use the standard deviation, right? So then we can add another line in the formula. When you have linear transformation, standard deviation will be a absolute value times standard deviation of the original one. Okay. By the way, the point here is you are taking absolute value here because it is always positive, right? Standard deviation should be always positive because it's the distance. So even if you multiply a negative number, the negative sign should be dropped. The negativity does not change the sign of the standard deviation, right? That's the only thing. I like pretty nice, so pretty nice property. So it's natural. And in the end, to summarize, how we calculate the standard deviation, just calculate the variance and then take a square root. So remember how we calculate the variance. We calculate the mean and transform all the observations to deviations, and then squared deviations, and then calculate mean of squared deviations. These are the steps for variance, and then just add another step at the end. And remember, we had, when you calculate the mean, we had sample variance or population variance formula, right? So remember, and sample variance is 1 over n minus 1, and population uses n in the denominator. So depending on which formula you use for the variance, standard deviation also follows those formula, right? Just take square root of them, right? So then we call sample standard deviation if you use n minus 1 in the denominator, and population standard deviation if you use n in the denominator. Again, which one is more commonly used? I would say sample standard deviation is more common in practice. Okay, I'm going to continue in the next video. Thanks for watching.